Solve problems on Introduction to Sequences. In this video, I discuss some basic problems regarding the definition of sequences. A sequence AN, that is A1, A2, A3 and so forth, is a rule that assigns a number AN to every positive integer n. Problems regarding sequences relate to how to find these rules. In these problems, we have to find first the general rule defining the given sequences. The first sequence is 1, 1/2, 1/6, 1/24, and so forth. We have to find an expression that produces these initial numbers. In problem 2, the sequence is 3, 3.1, 3.14, 3.141, 3.1415, and so forth. In problem 3, the sequence is 2, 5/4, 10/9, 17/16, and so forth. So all these sequences are defined by certain rules, and we have to look for the simplest possible rules that give these beginnings of sequences. This sometimes may be rather difficult. It is also ill-posed in the sense that there are, of course, several different rules that produce the first 4 or 5 terms that are given here for the sequence in question. In problem number 4, we take n as a seed for a sequence, and we form the sequence Sk by setting S1 is n, and then we use the rule Sk plus 1 is Sk divided by 2 if Sk is even, and Sk plus 1 is 3 times Sk plus 1 if Sk is odd. And we start with n being 3, and our task is to compute this sequence Sk. Now clearly, if Sk is odd, then 3 times Sk plus 1 is even, and all these numbers in this sequence are integers. We have to figure out how this sequence goes, what the sequence is, if we start with n equals 3. In problem number 1, we consider the sequence 1, 1/2, 1/6, 1/24, and so forth. We have to find the general rule that defines this sequence so that we actually can say and so forth. So we have to find the expression AN that gives 1, 1/2, 1/6, 1/24 when n is 1, 2, 3, or 4, and which expression is simple. So we look at the denominators, 1, 2, 6, and 24. 1 is, of course, just 1 times 1. 2 is 2 times 1. This seems completely silly and obvious. But 6 is 3 times 2 times 1. And 24 is 4 times 6. That is 4 times 3 times 2 times 1. So these numbers 1, 2, 6, and 24 appearing in the denominators, they are just factorials of 1, factorial of 2, factorial of 3, and factorial of 4. Factorial of an integer n is the product of all integers up to that number n. So the answer is that the general nth term of this sequence is just an is 1 over factorial of n. And this is a simple formula that obviously gives the beginning of the sequence 1, 1/2, 1/6, and 1/24. In problem number 2, the sequence starts 3, 3.1, 3.14, 3.141, and 3.1415, and then and so forth. What is this sequence? We have to remember that the mathematical constant pi starts 3.141592653589793284 6246, and so forth. So what we are looking at in the sequence number 2 is the beginning of this decimal point expansion for this mathematical constant pi. So the general nth term of this sequence is n first numbers of the decimal point expansion of pi. So this is the rule how we form this particular sequence, and the limit of this sequence is of course pi. In problem number 3, the sequence starts 2, 5/4, 10/9, 17/16, and then so forth. So what is a general term defining this sequence? So we have to figure out a nice expression for an that gives 2 when n is 1, 5/4 when n is 2, 10/9 when n is 3, and so forth. Now clearly this an is fn plus 1 divided by fn for some expression f. So for some function f. So we have to figure out what this function f might be. And we observe that f1 must be 1, f2 is 4, which is 2 squared, f3 is 9, which is 3 squared, and f4 is 16, which is 4 squared. So obviously fn is n squared, and the answer is that this sequence consists of numbers n squared plus 1 divided by n squared, which is also 1 plus 1 over n squared. In this problem, a positive integer n is a seed for a sequence sk, which is defined by setting s1 equals n. And sk plus 1 is sk divided by 2 if sk is even, and sk plus 1 is 3 times sk plus 1 if sk is odd. Now n is 3, our task is to compute the sequence sk. So we start with s1 being 3, and the rules were that sk plus 1 is sk divided by 2 if sk is even, and sk plus 1 is 3 times sk plus 1 if sk is odd. And we have to compute the sequence sk. So let us simply compute terms. We have s1 is 3, 3 is an odd number, so s2 is 3 times s1 plus 1, which is 10. 10 is an even number, so s3 is s2 divided by 2, which is 5. 5 is an odd number, so s4 is 3 times s3 plus 1, but s3 is 5, so 3 times 5 is 15 plus 1 is 16, so s4 is 16. s5 is 8, s6 is 4, s7 is 2, and s8 is 1. And after that, the sequence continues in a periodic way, so we observe that the sequence sk is 3, 10, 5, 16, 8, 4, 2, 1, and when we get to 1, then it repeats 4 to 1, 4 to 1 infinitely often. So this is the sequence sk. To figure out whether all seeds lead to this sequence ending by 4 to 1, 4 to 1, and so forth is an open mathematical problem. Let me know if you solve it.